fellow learners. Now welcome to the second lecture of the series in oils and fats. We have generally discussed the properties of oils and fats. Now we are going to take up some properties in details. Let me start with hydrogenation of oils. Some of the cooks prefer solid fats instead of liquid oils for cooking purposes. Accordingly, a large amount of groundnut oil, seed oil, etc. are hydrogenated in presence of suitable catalysts to obtain solid edible fat called vegetable ghee. As a result of hydrogenation, the melting point of the oil is raised and it is converted into an edible fat. In other words, hydrogenation is the process of converting an oil into a fat. Hydrogenation or hardening of oil is a process in which various unsaturated radicals of fatty glycerides are converted into more highly or completely saturated glycerides by the addition of hydrogen in the presence of a catalyst. The process of hydrogenation also improves the keeping quality, taste and odor of many oils. For example, whale oil and linseed oil cannot be used as edible oils because of their bad odor and taste. On hydrogenation to a proper degree, these oils can be converted into edible fats. The whale oil and cottonseed oil also give good hard soap when hydrogenated to a proper degree. The process of hydrogenation is carried out by passing hydrogen gas through the oil kept at about 140 to 180 degrees centigrade and containing finely divided nickel in suspension until the absorption of hydrogen takes place as indicated by the determination of iodine value. Now let us discuss in detail the optimum conditions required for the process of hydrogenation. Number one is that the hydrogen must be very pure. The hydrogen needed for hydrogenation of oils may be manufactured by a number of methods, but hydrocarbon steam process has widely been used. Traces of gaseous sulfur compounds like H2S, SO2, etc., arsenic, phosphorus and chlorine compounds, even carbon monoxide are strong catalyst poisons. It is therefore essential that the hydrogen should be completely free from these poisons as well as of taste producing substances. Impure hydrogen gas containing say H2S, PH3, CO, etc. is impregnated with electrolytic hydrogen and oxygen. The mixture is then heated over a platinum gas acting as a catalyst. The impurities burn along with some hydrogen and form CO2, SO2, P2O5, etc. This resulting gaseous mixture is then allowed to pass over quicklime, as a result of which moisture and acidic oxides are absorbed, and now the pure hydrogen thus obtained is used for the process of hydrogenation. The second point is that the oil also must be very pure as well as free from fatty acids. Fatty acids react with nickel and its oxide to form nickel soap, which is soluble in the oil. Soluble nickel compounds present in the edible oil act as poison and hence they should not be present in the oil. For purification of oil, the oil is taken in a tank fitted with steam coil and heated to about 30 degrees centigrade. Now calculated quantity of caustic soda solution is added to it. The mixture is then agitated for about 15 to 20 minutes by passing compressed air. The mixture is then allowed to settle and the oil is siphoned off from the impure aqueous alkali layer in a kettle. The oil in the kettle is washed with water several times to remove alkali. The moisture is removed by heating the oil at about 50 degrees centigrade and agitating the oil with compressed air. The last traces of moisture are removed by heating the oil in vacuum. It should be noted that oil should be free completely from the moisture, as the moisture may hydrolyze the oil at high temperature and pressure to form fatty acids. This is the plant for hydrogenation of oils. Here in the right corner, it is the tank where the hydrogenated oil is collected. In order to prevent the pyrophoric nickel from catching fire, the nickel catalyst is carefully transferred to the oil out of the contact with air. In order to keep the nickel particles in free suspension and to bring the oil in close contact of hydrogen, the mixture of oil, hydrogen and catalyst is agitated. Now, third point is the preparation of catalyst. First was the purification of hydrogen, second was the purification of oil, now it is the preparation of catalyst. The catalyst used is either added in the form of nickel oxide or nickel formate, which is reduced to metal by hydrogen gas, or it may be in the form of Rene nickel. 100 parts of a highly saturated oil or the oil to be hydrogenated and 1 part of the nickel formate are introduced into a specially designed vessel provided with temperature control arrangements. The change is then heated as quickly as possible to about temperature 375 degree Fahrenheit. At about 300 degree Fahrenheit, the decomposition of nickel formate takes place according to the reaction which is shown below here, and the nickel catalyst is formed. The charge is kept at maximum temperature for about 1 hour and then cooled. During the reduction and cooling period, hydrogen gas is passed through the oil in order to sweep decomposition products from the oil. After complete reduction, the charge may be pumped directly to the converter or may be formed into blocks, flakes or granules. Finally, divided nickel is obtained by this method, and this is again the picture of the plant for hydrogenation of oil. Nickel catalyst may also be prepared by careful reduction of nickel oxide by hydrogen at about 250 to 300 degrees centigrade. In order to have active catalytic property, the metallic nickel must be finally divided and should be reduced at a low temperature. At very low temperature, the nickel oxide will not reduce completely into metallic nickel. At very high temperature, say 400 degrees centigrade and above, it becomes completely inactive as a result of formation of grey nickel. Thus, nickel oxide is heated in a current of hydrogen in a closed vessel at an optimum temperature of about 250 to 300 degrees centigrade. That means the temperature which is neither too low nor too high. When hydrogen passes out without absorption, the reduction is supposed to be complete. The nickel is cooled in the current of hydrogen. Nickel catalyst can be prepared by precipitating nickel salts on inert porous carrier and then reducing it at high temperature in a current of hydrogen. Rene or spongy nickel is obtained by treating a powdered alloy of nickel and aluminium with caustic soda. As a result, Rene or spongy nickel is obtained when the sodium aluminate is washed out with water. Rene nickel is a high surface area catalyst. Nowadays, palladium has been found to be more effective than nickel as a catalyst, and the reaction takes place at lower temperature and takes less time. But because of the high cost of palladium, it is rarely used. The process of hydrogenation of oils is an exothermic process. According to Le Chatelier's principle, which we all have earlier studied, the exothermic reaction is favored by low temperature, but the rate of reaction decreases with decrease in temperature. Hence, it is necessary to select an optimum temperature at which the yield is maximum in minimum time. The optimum temperature in this case is between 140 to 180 degrees centigrade. The rate of reaction between hydrogen gas and oil may be expressed with this equation. The rate of reaction increases with the increase in molar concentration of reactants at a constant temperature. It is not possible to vary the concentration of oil by varying the pressure, whereas concentration of hydrogen gas can be increased by using hydrogen at high pressure. The hydrogenation reaction is reversible and takes place with a decrease in number of gaseous molecules in the product. This shows that increase of pressure will shift the equilibrium to the right. This can also be explained with the help of Le Chatelier's principle. Hence, hydrogenation process is favored when hydrogen under pressure is used. There are two processes of hydrogenation of oil, the dry process and the wet process. Here are the 6 reaction conditions now summarized from what we have discussed earlier for the process of hydrogenation. Now, it is another interesting property of fats and oils which is known as rancidity. Though in my first lecture we have talked a little about rancidity, let us now talk in detail about rancidity. It may be regarded as deterioration of odor and flavor of oils and fats. The susceptibility to rancidity is enhanced by the presence of unsaturated fatty acids in the glycerides and increases with the degree of unsaturation. Rancidity sets in more readily in oils and fats which have not been sufficiently freed from enzymes and other aggravating substances which are often present in oils and fats because they are first obtained from the sources in which they occur. For example, in case of the butter fat, the glycerides may be partially hydrolyzed in the presence of moisture so that free fatty acids appear, and in the case of butter fat, the odor of butyric acid will give the impression that rancidity has set in. In other glycerides, hydrolysis may liberate small amounts of partially odorless fatty acids, and from this stage, complex changes may occur, leading to some breakdown of the carbon chain, forming usually the volatile acids and aldehydes. The rancidity can be judged not only by odor but by chemical tests also. Physicochemical change in the natural properties of the fat leading to the development of unpleasant odor or taste or abnormal color, particularly on aging after exposure to atmospheric oxygen, light, moisture, bacterial or fungal contamination and or heat. Saturated fat though resist rancidity more than the unsaturated fats that have double bonds. We can classify rancidity as hydrolytic rancidity, oxidative rancidity and ketonic rancidity. Talking about the hydrolytic rancidity, it results from the slight hydrolysis of the fat by lipase from bacterial contamination, leading to the liberation of free fatty acids and glycerol at high temperature and moisture. Hydrolytic rancidity, volatile short-chain fatty acids with unpleasant odors are formed. Talking about the oxidative rancidity, oxidation of fat or oil catalyzed by exposure to oxygen, light and or heat producing peroxides derivatives which on decomposition give substances, for example, peroxides, aldehydes, ketones, and dicarboxylic acids that are toxic and have bad odor. It occurs due to oxidative addition of oxygen at double bond of unsaturated fatty acid of oils. Now talking about the ketonic rancidity. It is due to the contamination with certain fungi such as Aspergillus niger on fats such as coconut oils. Ketones, fatty aldehydes, short-chain fatty acids and fatty alcohols are formed. Moisture accelerates ketonic rancidity. Now the causes of rancidity can be summarized as exposure to light, oxygen, moisture, high temperature, bacteria or fungal contamination. Now, how can we prevent rancidity? Number one is the good storage conditions. Avoidance of the causes by keeping fats or oils in well-closed containers in cold, dark and dry place. Second is removal of catalysts. We can remove catalysts like lead and copper that catalyze rancidity. Addition of antioxidants, it prevents peroxidation in fats. They include phenols, naphthals, tannins and hydroquinones. The most common natural antioxidant is vitamin E, that is important in vitro and in vivo. Refrigeration also reduces the rate of most reactions that take part in rancidity. Now, hazards of rancid fats. The products of rancidity are toxic, that is, they cause food poisoning and cancer. Rancidity destroys the fat-soluble vitamins like vitamin A, D, K and E, which are required by the body. Rancidity destroys the polyunsaturated essential fatty acids. It also causes economical loss because rancid fat is inedible and that product will have to be discarded. Now, we will talk about analysis and identification of oils and fats. Fat constants or numbers are tests used for checking the purity of fat for detection of adulteration, to quantitatively estimate certain properties of fat, to identify the biological value and natural characteristics of fat, and detection of fat rancidity and presence of toxicity. First, we'll talk of saponification value. It indicates the average molecular weight of a fat or oil. The saponification value may be defined as the number of milligrams of KOH needed to neutralize the fatty acids obtained by complete hydrolysis of 1 gram of an oil sample. Thus, saponification values gives us the information whether an oil or fat contains high proportion of lower or higher fatty acids. In practice, a known amount of the oil or fat is refluxed with excess amount of saturated alcoholic potash solution, and the unused alkali is then titrated against a saturated acid. Since butter has a large proportion of lower fatty acids than lard and tallow, the former has high saponification value. Coconut oil has a comparatively higher saponification value 250 as compared to olive oil that has 200 and castor oil that has a saponification value of 180. Now let us discuss the lab procedure to find the saponification value. About 2 grams of the given oil or fat is taken in a conical flask and weighed accurately, say it is W gram. The oil or fat is then dissolved in about 25 ml of 0.5 normal alcoholic potassium hydroxide solution. Then the reaction mixture is refluxed using a water condenser on a water bath for half an hour. The resulting solution is cooled and titrated against a 0.5 normal HCl solution, adding 1 ml of phenolphthalein as indicator. The number of ml of acid required is noted. Let this volume be V1. An exactly identical blank experiment, that means we leave the fat or oil part, is performed. Number of ml of hydrochloric acid required is noted, and let that volume be V2. The saponification value is given by this formula, V2 minus V1 into normality of HCl into equivalent weight of KOH upon weight of the oil sample, which was W gram. Now, molecular weight of oil sample can again be calculated putting the value of saponification here. We multiply it by 1, 2 or 3 if we are dealing with mono, di or triglyceride respectively. Now coming to acid value. It indicates the proportion of free fatty acid in the oil or fat and may be defined as the number of milligrams of caustic potash required to neutralize the acid in 1 gram of the sample. The normal acid value of most sample lies within 0.5. If any titrable acid other than a fatty acid is present in the sample, it will be an error. Now the procedure: weigh about 20 grams of the oil or fat into a 250 ml of conical flask. Add about 50 ml of 95% alcohol that has been neutralized with 0.1 normal alkali solution using phenolphthalein indicator. Heat the contents to boiling and shake the flask thoroughly in order to dissolve the free acid as completely as possible. The solution is cooled and then titrated again 0.1 normal alcoholic caustic potash solution with constant shaking using phenolphthalein as indicator until the pink color persists after vigorous shaking. For good results, always keep the solution hot even if no precipitation occurs, because oils containing much fatty acids when titrated with alkali give soaps that precipitate on cooling and occult some of the solution. Heating makes the soluble so that the titration may be completed, so we keep the solution hot. Endpoint is supposed to be reached when the pink color persists for 30 seconds in the hot solution after vigorous shaking. If the sample is largely fatty acid, satisfactory results are obtained with 1 to 2 gram of the sample. Now the calculation for acid value: the fatty acid present may be expressed as the degree of acidity, which is defined as the milliliters of normal alkali required to neutralize the free acids in 100 gram of fat or oil, which is now given by this formula: ml of alkali into normality into 100 upon weight of the sample of oil or fat. The key difference between the acid value and saponification value is that acid value gives the mass of potassium hydroxide that is required to neutralize 1 gram of the chemical substance, whereas saponification value gives the mass of potassium hydroxide required to saponify 1 gram of fat. Now one important number, which is the iodine number or iodine value. It shows the degree of unsaturation of the constituent fatty acids in an oil or fat and is thus a relative measure of unsaturated bonds present in the oil or fat. Iodine value is expressed in grams of iodine absorbed by 100 grams of oil or fat. Unsaturated compounds absorb iodine in suitable form and form saturated compounds. The amount of iodine absorbed in percentage is the measure of the unsaturation in the oil. No oil has zero iodine value, and oils are classified as drying, semi-drying and non-drying on the basis of their iodine value, which we discussed in our first lecture. The greater the iodine value, the more unsaturation and the higher the susceptibility to oxidation. Oleic acid containing one double bond absorbs 90% of the iodine. Linoleic acid, two double bonds, absorbs 181% iodine, and linolenic acid, which contains three double bond, absorbs 274% iodine. Non-drying oils have one double bond and absorb iodine below 90%. Semi-drying oils contain some proportion of double bonds and have a iodine value below 140. Oils containing some proportion of triple bond and having iodine value above 140 are called the drying oils. The iodine value for coconut oil is 8, for olive oil is 88, for human fat is 105, and for linseed oil is about 200. So, we have studied about the saponification number or saponification value. We have talked about the iodine number or iodine value. We have talked about the acid number or the acid value, which tells us about the different properties of fats and oils. So I can tell you, as we summarize, in the two lectures of fats and oils, we have taken up a number of topics, starting from the definition, distinction, properties of fats and oils, then the classification of fats and oils, fat splitting. Out of the number of properties which we studied regarding the fats and the oils, we have discussed in detail the hydrogenation of oils and the optimum conditions required for the hydrogenation of oils, in which we talked about the purity of hydrogen, purity of oil sample, and preparation of the catalyst. Then in rancidity, we talked about the types of rancidity, hydrolytic, oxidative, ketonic, then the causes of rancidity, prevention of rancidity, and we also discuss the hazards of rancid fats. 3 important values which we calculate in the lab as well have also been discussed with you all: saponification value, iodine value, and acid value. With this, I conclude the topic of oils and fats. In the next topic of applied chemistry, we will be continuing the lecture. Thank you.